Hey everyone, welcome back to the Deep Dive. We're diving into a paper today called Polynomial Threshold Functions of Bounded Tree Width, Some Explainability and Complexity Aspects. I know, the title. It sounds a little intimidating maybe, but trust me, this is really cool stuff.
Yeah.
We're talking about like how AI actually makes decisions, like how does a self-driving car know when to hit the brakes? Or like how does an algorithm figure out what you're going to buy online? That's what this paper gets into, but with a really interesting twist.
Yeah, the twist is all about explainability. See, right now, a lot of AI models are kind of like these black boxes. They work, but we don't always know exactly why. So this paper, what it does is it explores a mathematical tool. It's called a polynomial threshold function, or PTF for short. And it just might help us crack open that black box and shed some light on how AI is actually making these decisions.
Okay, so time out for a sec.
Okay.
What exactly is a polynomial threshold function? Because it does sound kind of, well, complicated.
Okay, so think of it like this. You're trying to decide if you want to go to a party, right? You're weighing all these different factors. Who's going to be there? What kind of music are they going to play? What's the weather like? Well, a PTF does something similar. But with math, it takes a bunch of variables, assigns weights to them, and then it uses a threshold basically to decide, like, party or no party. And this paper, it focuses specifically on Boolean PTFs, where the variables are true or false, like a light switch. It's either on or it's off.
Gotcha. So how does this all connect back to helping us understand AI?
So a lot of AI models, especially the ones that classify things like spam filters or those medical diagnostic tools, you can actually represent them as PTFs. And so by understanding like the structure of those PTFs, we can potentially figure out how those AI models are reaching their conclusions.
Ah, okay. So it's kind of like looking at the blueprint for how the AI makes up its mind.
Exactly. Now, this paper, it introduces this concept they call tree width. It's basically a way to measure how complex a PTF is. Think about it like a family tree, right? A simple one is easy to follow, but one of those massive ones with like a zillion branches gets kind of confusing. Well, tree width is kind of like that. It measures how tangled up the logic of that PTF is.
Okay, so a high tree width means the decision process is more complicated.
Exactly. And that's where explainable AI really comes into play. What this paper is saying is that PTS with lower tree widths, they're just easier for us to wrap our heads around. And they even suggest using a tool called an ordered binary decision diagram, or OBDD for short, to visualize these PTFs.
OBDDs. Now that sounds even more complicated than PTFs.
Don't worry, they're not as scary as they sound. Just think of them as flowcharts. You know, they visually represent all the steps in your decision. So instead of this mysterious black box, we get a clear picture of how the AI got to its answer.
So it's like giving the AI a way to show its work, which makes a lot of sense, especially in areas like medicine, right, where you definitely want to know why the AI is giving you a certain diagnosis. You wouldn't want a doctor just blindly trust in it without understanding the reasoning behind it.
Exactly. And that's why this whole idea of explainable AI is getting so much attention these days. But there's kind of a catch. See, representing really complex AI models as OBDDs, it can take a ton of computing power. Those flowcharts can get, well, absolutely enormous.
So how do we get around that?
Well, that's another really clever thing this paper does. They propose a way to approximate it, basically balancing accuracy and efficiency. It's kind of like saying, okay, we don't need to capture every tiny detail in the OBDD. Let's find that sweet spot where it's still super useful for understanding the AI, but it doesn't need a supercomputer to run.
That's smart. Like a map, right?
Yeah.
You don't need to see every single tree and house, just the main roads and landmarks to get where you're going. So they got these PTFs, tree width, and OBDDs. What else are they looking at in this paper?
Okay, so to really test out these ideas, they use this type of AI model. It's called a Bayesian network classifier, or BNC for short. BNCs are amazing at classifying things, but explaining how they do it. Well, that's the tricky part. So the researchers, they're basically using these BNCs as like a test case to see if their approach with PTFs and OBDDs can actually make these BNCs more explainable.
So if it works with BNCs, it could potentially work for other types of AI models too.
Exactly. It's like finding a key that could unlock a whole bunch of doors.
Okay, now I'm really seeing how this paper could be a game changer. But before we get too far ahead of ourselves, they mentioned a specific example of a PTF in the paper. What's up with that?
Right. So they use this function. It's the sign of by 1 plus by 2 plus by 3 plus by 4 by 1 by 2 by 3 by 4 of 2. Now, I know it looks like a jumble of symbols and stuff, but it actually shows how a PTF can represent a really specific decision.
Okay, break that down for me. What's that function actually doing?
Okay, so imagine you have 4 light switches, right? By 1, by 2, by 3, and by 4. This PTF, it'll only output a 1 or a yes if at least 3 of those switches are flipped on. Or get this. It'll also say yes if both pairs of switches by 1 by 2 and by 3 by 4 have exactly one switch flipped on. It's showing how a PTF can capture those trickier if-then scenarios.
So it's not just about the individual variables themselves, but also how they relate to each other. Kind of like ingredients in a recipe, right? The individual ingredients are important, but it's how you combine them, how they interact, that makes the dish.
Perfect analogy. And that leads us to another cool detail from the paper tree, augmented naive Bayes classifiers. TNs for short, they're like a special kind of BNC. And you can represent them as quadratic threshold functions, or QTFs.
Well, hold on, more acronyms. What are QTFs and why are they important here?
Oh, okay. So picture a TAN like a family tree. Okay. Each person is a variable, and the lines connecting them, those are the relationships. A QTF basically captures those relationships mathematically. The quadratic part means it's looking at pairs of variables, like the parent-child relationship or the sibling relationship in that family tree.
So the QTF's kind of like mapping out all those connections within the TAN.
Yeah.
And that helps us see how the TAN is making its decisions.
Precisely. And the researchers, they take it a step further. They actually do this small experiment. They use a specific TAN structure. You can actually see it in figure 2 of the paper. And they train a simpler AI model on the data from this TAN. It's called a generalized additive model with interactions, or GA2M.
GA2Ms. Got it.
Yeah.
So what happened in the experiment?
What's really cool is that the GA2M often learned these interaction terms that were super similar to the original TAN structure. It's like the GA2M, even though it's simpler, it could still pick up on the same key relationships that were encoded in the TAN.
That's wild. It's almost like this whole approach with PTFs and OBDDs could actually reveal the hidden logic of these more complicated AI models.
Yeah.
Even if they weren't designed that way in the first place.
Exactly. And that opens up some really exciting possibilities.
Which is a perfect segue to our novel notions segment, where we get to brainstorm and explore those intriguing questions and potential research directions inspired by the paper. This is where things get really fun.
I know, right? Because if we can represent these AI models as PTFs and measure their complexity using things like tree width, it makes you wonder, are there even better ways out there to understand and explain these super complex systems?
Ooh, I like where you're going with this. Tell me more.
Well, one thought is like, could we go beyond just tree width? I mean, it's a good starting point, yeah.
Oh.
But maybe there are other ways to measure how complex a PTF is, ways that are like more nuanced, more about how explainable it actually is.
So instead of just looking at how tangled the logic is, we can look at other things. Like what kind of things are we talking about here?
Okay, so let's say you have two PTFs and they have the same tree width, right? But one of them has like just a few really strong connections between its variables, while the other one has a ton of these weak kind of spread out connections. Even though their tree widths are the same, the one with the strong connections, it might actually be easier to understand, right? Because it's more focused.
Yeah, that makes sense. It's kind of like the difference between like a really clear, concise argument where they make a few really strong points versus like a rambly one that throws all these ideas at you, but they never really connect.
Exactly. So maybe a complexity measure that looks at like the distribution of the weights within the PTF, that might be way more informative. Like how concentrated are those weights? Or are they all spread out?
That's interesting. So it's not just about how many connections there are, but also how strong those connections are. What else could we look at?
Okay, this might sound a little out there, but what about the meaning of the variables?
Wait, hold on. You're saying that the actual meaning of the variables could affect how easy it is to understand the PTF? How does that work?
Okay, so think about it this way. If the variables in a PTF represent things that are already like connected in our brains, even a really complex PTF might be easier for us to grasp because we can relate it back to what we already know.
Okay, give me an example.
All right, so let's say we have a PTF that's deciding if you should go for a run, okay? The variables are things like, what's the weather like? How much energy do you have? How much daylight is left? Those are all things that we just intuitively understand as being connected to running, right?
Yeah, I can see that.
Okay, now imagine another PTF, and it has the same tree width, but this time the variables are totally random stuff, things that don't really seem connected at all. Like, I don't know, the price of tea in China, the number of birds singing outside, and the color of your socks. Even if that PTF itself isn't that complex, it'd be way harder to explain because those variables just don't make sense in the context of run-in.
So the context of the variables is really important. If we can connect the PPF to something we already get, it becomes more transparent even if the math behind it is complicated. That's super cool.
Right. It opens up a whole new way of thinking about these complexity measures. But here's another novel notion that I think is really exciting. What if we could actually use this whole connection between PTFs and BNCs to design a totally new kind of machine learning model?
Whoa, okay, now you're talking. So you're saying we could create AI models that are like explainable from the very beginning, like by design.
Exactly. What if, instead of trying to make our current AI models more explainable after we've built them, we just built them from the ground up with explainability in mind?
So instead of starting with that black box and trying to pry it open, we just designed the box with see-through walls from the start.
Exactly. And since we already know that PTFs can represent these super complex AI systems, and we know that we can analyze their structure to figure out how explainable they are, why not just make the PTF the foundation of the whole model?
So the AI's decision-making would be like inherently transparent because it's based on this mathematical framework that we can actually understand and visualize.
Right. Just think about what that could mean for something like healthcare. Imagine a medical diagnosis AI that not only gives you the diagnosis, but it actually shows you the decision process as a PTF. You could literally see which factors it considered, how much weight it gave each factor, and how all of that led to the final diagnosis.
That would be a game changer for trust in AI in medicine. Doctors could actually understand how the AI is making its decisions. Patients would feel more confident in the diagnosis. And you could even use it to spot potential biases or errors in how the AI is thinking.
Exactly. And it's not just healthcare, right? Think about finance, criminal justice, any area where the stakes are high and people need to know why AI is making decisions that could have a huge impact on their lives.
For sure. Of course, there are going to be challenges, right? Like designing these explainable by design models is going to require some totally new ways of thinking about AI training and optimization. We'd have to figure out how to make them just as accurate as our current models, but without sacrificing that transparency.
Absolutely. And then there's the whole question of how do we actually present all this information to users in a way that they can understand and actually use? It's not enough to just throw a bunch of equations at them, right?
Yeah.
We got to translate it into something that's meaningful and relatable.
That's a great point. But the potential here is just massive. It's a super exciting direction for the future of AI.
It really is. And speaking of exciting directions, this paper also dives into this really interesting question about the complexity of different types of PTFs. They look at these things called positive PTFs, where all the weights are positive numbers, and they compare them to general PTFs, which can have both positive and negative weights.
Hold up. Why does it matter if the weights are positive or negative?
Well, it turns out that positive PTFs can actually be way more complicated than general PTFs, even when they're representing the exact same function. It's kind of trying to explain a really complex idea using only positive words.
Yep.
You can do it, but it might take you a lot longer and get kind of convoluted.
So are positive PTFs just a bad idea then? Why even use them?
Well, they definitely have their uses in certain situations, but the point the authors are making is that understanding those differences in complexity between positive and general PTFs, that's really crucial for building AI systems that are both efficient and explainable. Like if you're working on a problem where you can use a general PTF, it's probably going to be a lot easier to understand and explain than if you're stuck using a positive PTF.
So it's all about picking the right tool for the job. If we understand the trade-offs, we can make smarter choices about which type of PTF to use and how to balance complexity and explainability. This is getting pretty deep, but I'm loving it. I feel like we're really starting to unpack some big ideas here about the nature of AI and how we can make it more transparent and accountable. But before we get too carried away, let's start wrapping things up for today.
Yeah, sounds good to me. We've covered a ton of ground today, and I'm really curious to hear what our listeners are thinking about all of this.
Me too. So all our listeners out there, hit us up. What are your novel notions about explainable AI? What other questions did this paper spark for you? Share your ideas and keep the conversation going, because this is just the beginning of a really important journey.
A journey toward an AI-powered future that's not just intelligent, but also one that we can understand and trust.
And on that note, we'll leave you with one final thought to chew on. As AI becomes more and more woven into our lives, understanding the why behind its decisions, it's not just a nice to have anymore. It's essential. It's about building trust, making sure things are fair, and ultimately creating an AI that benefits all of us.
Until next time, keep those minds curious and keep exploring.
So there you have it. We went deep, deep down into the world of polynomial threshold functions, tree width, OBDDs, and a whole bunch of other fascinating concepts that might just hold the key to unlocking the secrets of explainable AI.
It's definitely complex stuff, But the exciting part is that researchers are out there right now working hard, developing these incredible tools and techniques to make AI more transparent, easier to understand.
And like we talked about, it's not just about satisfying our curiosity, right?
Hmm.
This has some serious real-world consequences, especially in areas like medicine, finance, criminal justice, anywhere that trust and accountability are super important.
That paper we explored today, Polynomial Threshold Functions of Bounded Tree Width, some explainability and complexity aspects. It's a perfect example of the kind of groundbreaking research that's happening in this field.
If you want to learn more, and we know you do, check out the full paper. We'll drop a link for you in the show notes.
And we want to hear from you. What are your thoughts, your own novel notions about how we can make AI more explainable, more trustworthy? Hit us up.
Do you think design in those explainable by design models is even possible? What are the biggest hurdles we got to overcome? Head over to our website, our social media channels, and let's get this conversation going, because this is just the start of a really important journey, folks.
A journey towards an AI-powered future that's not only intelligent, but also understandable, and something we can all trust.
Absolutely. And with that in mind, we'll leave you with this. As AI becomes more and more integrated into our lives, understanding that why, understanding the reasons behind its decisions, it's not a luxury anymore. It's a necessity. It's all about building trust, ensuring fairness, and ultimately creating an AI that benefits every single one of us.
Keep those minds curious, everyone. Keep asking those tough questions, and keep diving deep. We'll see you next time.